All right. Good morning, everyone, or good afternoon, depending where you are. It's a great pleasure for me to introduce Sebastian Eterović from UC Berkeley, and he'll speak about existential closedness and differential algebra.
Thanks a lot, Ronnie. So yeah, thank you very much for the invitation to speak here today. It's a great pleasure. I want to talk about this problem in arithmetic geometry, which is usually referred to as existential closedness, and specifically, the different ways in which differential algebra has allowed us to get close to solving this question in certain cases. So in order for me to introduce the problem, I want to start by talking about the exponential function, which hopefully, I think everybody knows about this function, and we've all encountered it at some point. So the exponential function is very interesting. It is very well behaved in many ways, in the sense, for example, that it's a holomorphic function. It satisfies a very nice differential equation. It is also transcendental, and so that means that you cannot construct this function only using field theoretic operations. You need some analysis to build it up. And despite the fact that it's a transcendental function, it still has interesting algebraic properties. Perhaps most notoriously, the fact that it transforms addition into multiplication. In that sense, you think of this as a group homomorphism. But because it's a transcendental function, then you don't expect it to have that many algebraic properties. And so any algebraic properties you find are probably interesting because there's not that many, so they must be meaningful in some way. And you might start wondering, well, how many are there? Like, could I go and try to find all of them somehow? And well, I already mentioned one at the level of the function. So functionally speaking, this is a group homomorphism. But then you could also wonder about, like, point to point. What are the algebraic properties of X? For example, could exponentiation take an algebraic number to another algebraic number? Okay, so Lindemann answered this question back in the 19th century. And he said the only way that happens is if you start with 0. 0 goes to 1, and that's it. Any other algebraic number is going to give you a transcendental number under exponentiation. Shortly after, Weierstrass expanded the theorem, and he considered finitely many algebraic numbers. And he said, okay, if those finitely many algebraic numbers happen to be Q linearly independent, in the sense that you're looking at this field as if it were a Q vector space, then the corresponding exponentials are algebraically independent over Q. Okay, so these are two very classical results about exponentiation to start us off. And so then lots of other problems about exponentiation showed up. Some were solved and some are still open. And one that was that stood out, I think, among many of the others was this thing called Shannon's conjecture. So this is a conjecture that appeared in the 60s, attributed to Stephen Shannon, but it appeared in a book of Lang on transcendental number theory. And the conjecture starts, I think, with the motivation from the Lindemann-Weierstrass theorem. It says, if you take some complex numbers now, which are Q linearly independent, then the transcendence degree generated by the field extension of those numbers under exponentials should be at least n. And well, this conjecture is still open. But one thing that people realized was that many of the other open problems of exponentiation could be settled if we somehow were able to prove this conjecture. So this garnered this conjecture a lot of attention and a lot of importance, I guess, in the realm of transcendental number theory. It seemed to be like a beacon, one of those things that you settle that and then you have a lot of other things just for free. And so you might start wondering, well, is that the only thing that we would like to know about the exponential function? Is it that this is the one question about exponentiation? Okay, so my point is that it's not. And in order to introduce another question that is not really, doesn't exactly follow from Shanwell, the first thing I want to do is I want to rewrite Shannon's conjecture in this other equivalent formulation. This is a more geometric formulation. So instead of having to look at transcendence degrees of field extensions, now you just consider algebraic varieties. So suppose you have an algebraic variety over Q, and somehow you know that this algebraic variety intersects the graph of exponentiation. Okay, well, if the dimension of the variety is less than n, then it must be that these numbers were Q linearly dependent. So here I'm writing the conjecture sort of in the contrapositive of what's written up there. And well, looking at the conjecture in this way, in this more geometric way, I think it's now not so hard to go into this counterpart problem, where you say now, in general, when would we expect a variety to intersect the graph of exponentiation? The graph of exponentiation is an analytic object, and it's a transcendental analytic object. And this V is an algebraic variety from the world of algebraic geometry. So when would those two things collide? What kinds of things need to happen for the variety V to even have a point like this? And so this leads us then into the question that I wanted to present today, which is existential closedness. So here I've summed existential closedness as EC. So formally speaking, existential closedness asks you to do the following thing. You need to find a minimal set of geometric conditions that the variety needs to satisfy so as to ensure that the variety has points like this, and also so that you don't like have any accidents. I wanted to have a Zariski dense set of points like this. And what that means is that there need to be lots of points in the variety, so that there's like a reason why the variety has that many points in the graph of exponentiation. Here, I've also started suppressing the indices. So now you need to think of Z as a tuple of elements. Okay, so this is existential closedness. This is a question that I think is like really started gaining momentum by the work of Boris Silber on pseudo-exponentiation. So in model theory, it is not so uncommon, really, it's very normal to wonder about existential closedness type problems, because you want to know whether or not your models are existentially closed, which essentially means that you are allowed to remove existential quantifiers, which concretely speaking, what it means is that you know when certain systems of equations have solutions. And so Boris Silber was working on the model theory of exponentiation, which in particular would allow us to have a complete axiomatization of the theory of exponentiation. And his work on pseudo-exponentiation shows that if you're allowed to somehow solve Shannon's conjecture and existential closedness, then that would really be sort of everything you would like to know about exponentiation. That gives you a complete axiomatization of the algebraic properties of the exponential function. Now, in order to do that, like Silber had to give a conjectural answer to this question. And here is his conjecture. He says, the geometric conditions that V has to satisfy are two. One is called rotundity and the other one is called freeness. Now, these are somewhat technical conditions, so I didn't want to write them down explicitly because it would take some time. But what they're trying to do is actually very natural. So the rotundity condition, for example, is there to ensure that certain dimensions are large enough. So the variety V, for example, under rotundity is required to have dimension at least n. And certain other varieties you can build out of V are also required to have a certain amount of dimension at least. And so rotundity is just that. It's just making sure that V and some other varieties you can build out of V have enough space for there to be points in the graph of this transcendental function. And then there is freeness. freeness is just there to ensure that you are not going to trivially break any functional properties that the exponential can have. So it's because it's really easy to come up with varieties which just do not intersect the graph of any function at all. For example, what you could do is you could say, suppose that v is given to us by two equations in 4 variables. So in the variables x1, x2, y1, and y2, suppose that v is given to us by the following 2 equations, which is x1 equals x2. So that would mean that the 2 arguments need to be equal, but then you require that y1 is not equal to y2. For example, y2 plus 1. Then this cannot intersect the graph of any function, because if it did, x1 and x2 would have to be the same, but then f of x1 and f of x2 cannot be the same. That cannot be a function, so yeah. Freeness is then here to ensure you're not doing silly things like this. So this here is not allowed under freeness. Okay, so this conjecture goes under many names. It's sometimes been called the exponential Nullstellensatz because it is a form of Nullstellensatz for systems of exponential polynomials. Now, as history would have it, the way that Silber originally attacked the question of studying the model theory of exponentiation was to consider this sort of older brother of existential closedness first. This conjecture, I think, came first. And well, we'll see later on that it turned out that you only needed to consider this one. But so let's talk about this older brother version. Here, you're asked to do sort of the same thing, but now you're not just satisfied with having many points in the graph of exponentiation. You want some of those points to be generic in V. And generic means of maximal transcendence degree. So the transcendence degree of this point needs to be equal to the dimension of V. Okay, so this is existential closedness. This is the question that I want to discuss today. Now, before we go into that, I just want to say that the way that I stated existential closedness here is an open-ended question. And my intention with that is to say that you might ask this question about many other functions. There are many functions in arithmetic geometry which are transcendental, holomorphic, if you restrict to maybe to a smaller domain, and that have lots of interesting algebraic properties. And so you might wonder, can I study all of them? Can I try to understand the existential closedness problem for all of those functions? And this is something that is being done. And what other kinds of functions might want to look at? For example, there are other kinds of exponential functions. So for example, there's the Weierstrass P function, which is associated to elliptic curves. Or more generally, in higher dimensions, you would have the exponential of an abelian variety or a semi-abelian variety. Both of these functions behave like group homomorphisms. But then there are things that are not like group homomorphisms. So for example, there would be modular functions. One of the most famous ones is this thing called the J function, which classifies elliptic curves and is defined on the upper half plane. And there's many other modular functions you might look at. There's also the higher dimensional analogs of modular functions, sometimes called automorphic functions, or also uniformization maps of Shimura varieties. I guess I'll write it like this. This is a Shimura variety. There's lots of, all of these functions are transcendental. They're all holomorphic. They all satisfy differential equations. Some of them are nicer than others, but still they all have the differential equations. And they all have interesting algebraic properties. So you might want to understand the theory of all of these things. And why not? And well, then you might get a little bit more ambitious and you might start going into things that are holomorphic and transcendental, but do not satisfy a differential equation. So why not, for example, work with the Riemann Zeta function? why not? And well, I totally agree. I think this should be done. But I would say that because this function doesn't satisfy a differential equation, it's sort of like on a different level of difficulty. Understanding existential closedness for these functions is already interesting enough, and it's proven to be difficult. This one here, I think, is going to be in a different level of difficulty. But I don't think it should not be done. I still think it would be a very interesting question to work with.
And Sebastian, just to clarify, it's open for all of these functions, right?
Full existential closedness, yes. It's open for all examples. But that doesn't mean that we don't know anything. So now I want to start getting into like, what can we do about these questions? So how is differential algebra going to help us with any of this? Okay, so I think the foundational stone on which all of the differential algebraic methods rely on when it comes to these kind of questions is this theorem, Axe channel. So shortly after Channel's conjecture showed up, there was a paper of James Axe in 1970, I think, that addresses Channel's conjecture. And it says that if you're working on function fields, so it means your elements are now power series, then Channel's conjecture is true over the constants. As long as you measure transcendence degree over the constants, then this field extension does satisfy the inequality of Channel. In fact, it satisfies a stronger inequality. Because you can put here also the rank of the matrix, the Jacobian matrix, the matrix of partial derivatives. Okay, excellent. This is a very good theorem. And the method that Axe used to prove this theorem was completely differential algebraic. So it was just using differential algebra. And in that sense, the theorem of Axe is really a theorem that can be stated abstractly in the setting of differential fields. So I have restated the same theorem here in the differential setting, where now you just work on a differential field with some derivations of characteristic 0. My differential fields will always be of characteristic 0. And you consider the corresponding field of constants. And then you say, suppose that I have some elements in the field which satisfy this. And this here is sort of saying that these points are related to each other as if they satisfy the differential equation of the exponential function. Okay, and then you also say, suppose that the x's are Q linearly independent. Then the theorem says the transcendence degree of this field extension is at least this much. And we're able to get this thanks to the fact that Axe's result is purely algebraic, differential algebraic. So, all right, this is all very nice. And you might think, well, okay, so why is Axe channel called Axe channel? Well, it should be, I guess, called the theorem of Axe. But it's a theorem of Axe about Channel's conjecture. And the people in arithmetic geometry that try to prove theorems like this have since then always referred to this type of theorems as Axe channel. And today we have lots of Axe channel theorems. For all of the examples that I mentioned in the previous slide, where you had differential equations, all of them now have Axe channel theorems. However, the proofs have not always been purely differential algebraic. For a while there, except for the exponential functions, the exponential and the exponential of algebraic groups, it seemed that if you wanted to get any other type of Axe channel theorem for like modular functions, for example, you needed to use ominimality. And so there were many theorems about Axe channel for these kinds of functions using ominimal methods. But fortunately, now recently, the work of Ronnie with James Freitag and Guy Casal and David Blasquez-Sanz has managed to produce an alternative proof for modular functions and other examples as well, which is now purely differential algebraic. Yeah. Well, in any case, even if you don't have a purely differential algebraic proof of X channel, normally, if you're able to have a good enough statement of the theorem, you are able to obtain a differential statement through other tricks. So in some sense, you can manage at the end of the day to try to get a version like this one. But okay, we have this differential version. How do we use it in the context that I was talking about? It seems like this theorem is sort of saying that we might expect Shannon's conjecture to be true. It's sort of like maybe you could try to argue that this is evidence for Shannon's conjecture, although it's not talking about exactly the same kinds of elements, because now here these are functions, and Shannon's conjecture was talking about complex numbers. But the point is that thanks to the differential version, you can actually bring it down to complex numbers. And this is because you can now build on the complex field these things called exponential derivations. So on the complex numbers, you can build continuum many linearly independent derivations, which satisfy this important property here, which I would say that is saying that the derivation respects the exponential function. Okay. So there are lots of these things. You can build these things not really constructively, but you can show that there's lots of them. Now, how do you do that? There are different ways of going about this, but I think that the more general method, the method that would work not just for the exponential function, but any of the other examples that we care about, is using ominimality. Yeah. But like I said, somewhat unfortunately, I guess the construction is not super constructive, in the sense that there's some steps there where you need to like take some kind of basis of the field, and the existence of that basis is given to you by, you know, like axiom of choice kind of arguments. Except for that, this is a fairly constructive way. The method is fairly constructive. And so you can now witness the complex numbers as a field with derivations which are interesting for the X channel theorem, because they satisfy this, which is exactly what the kind of thing you needed for X channel. You can consider the corresponding field of constants, which would be this thing, and it happens that this is now a countable field. And so if you just take the differential form of X channel and you apply it to this setting, what you're going to get is that Shannon's conjecture is true if you stay away from this field. If the elements, the complex numbers that you work with are not in this field, then Shannon's conjecture is true. In fact, a stronger inequality is true. So that is sort of saying that essentially there's only at most countably many counterexamples of Shannon, if there are any. So this is a very concrete way, I think, now in which we can say that, yes, Shannon really is saying that we should believe in Shannon's conjecture, for the most part, at least. Okay, cool. Now, like I said, okay, so the construction of these derivations is perhaps not super explicit, but I can give you a more algebraic description of this set, which I've written here in this theorem. So how do you know whether an element is in this weird set? Well, what has to happen for an element to be here is that it has to be in some sense algebraic over the exponential function. And what that means is that you're able to find some elements, some complex numbers, the first one of which is the z that you're working with, and then some polynomials with rational coefficients, so that when you evaluate these polynomials in this specific kind of tuple, all these polynomials vanish, and the Jacobian of the corresponding system does not vanish at this point. So this is normally referred to as a Hovansky system of exponential polynomials. If you're able to find a system like this, where the solution of the system has as one of its coordinates the point z, then that means that z is in this field of the things that are algebraic with respect to exponentiation. So this is a theorem that was originally proven by Jonathan Kirby for the exponential function, but his method was not really well suited to be extended to other situations, specifically modular functions. It just, I don't know, I tried and I failed. So along
Can
with—
I ask a question about the system?
Yeah.
So is, just because it's not totally clear, is does it end up giving you a Pfaffian chain or no?
Good question. So for the exponential function, it should, yes, because, but I'm not sure if that's true in general, because wouldn't that imply, so if somehow there's a formal proof that this gives you a Pfaffian chain, that would imply that the same is true regardless of who was here, no? And then like that would settle whether or not the J function is Pfaffian.
Oh, but the J function's not Pfaffian.
Right. So, okay. So the J function, okay. So yeah, good point. So it's not Pfaffian. So I don't think that's just, so that is, this gives you a Pfaffian chain maybe for exponentiation, but that would be because exponentiation is Pfaffian.
Oh, right. Yeah, that's essentially what I was asking, though. So the elements, I think you're calling them A1 to AN. Is that right?
Yeah.
They, with respect to this weird derivation that you've set up, yeah. They're solutions to some Pfaffian type equations, it seems.
Well, okay, yes. Now, well, so, okay, my point is that I guess what I would say is that this statement that I wrote here is still true if you replace X with J.
Oh, I see.
So you can build derivations that respect the J function and all of the derivatives of the J function. And saying
yeah.
that you're
sure, right. Sure. I'm not saying that it's Pfaffian just because of what you've written down, but because you used the exponential function there as well as what you've written down.
Yes.
Okay, yeah. So sorry, that's why it wasn't totally clear to me. I'm not sure about that, by the way. I was just asking if it was.
All right. But I think that's correct. Yes. All right, thanks.
Excuse me, I have a quick question. How does N depend on this? Is it uniform or it depends on Z?
Well, there's many values of N that are going to work. You just want some N. So saying that there is a Z here means that there is some N that works.
Okay.
But that's not unique. It's like saying, for example, how do you know if a certain number is algebraic over a field? Mm-hmm. Okay, there is a canonical N to choose, which would be the degree of the minimal polynomial, but there's more than that, right? So any multiple of the minimal polynomial will work. Yeah.
But does N measure something about Z?
Yeah,
I guess just it's algebraic. It's how algebraic it is over.
Right.
Yeah. Okay. Okay.
Yes. So definitely the minimal N here is an important number about Z that one could try to understand a little bit better. So yeah, as I was saying, so this theorem that I've written here for the exponential function was first proven by Jonathan Kirby. And his proof works really well for exponential functions, but not so well for anything else really. And so along with Vahagan Aslanian and myself, we tried to come up with a proof that would work more generally. Sort of like as long as you have an X-channel theorem, you should be able to produce all of these constructions. And we did, fortunately, in the end. So here, when I write this, what I mean is, if we're now focused more on all of the examples I mentioned earlier, certainly you would not try to study them sort of like one at a time, because that's going to take too much time. You would like to have general methods to try to understand these things, sort of hopefully, so in some ways, maybe you would expect all exponential functions together. Hopefully you can understand them all in some way. And then all modular functions together in some family. Hopefully all the methods would work, the same methods would work for all of them, and so on. So you can group them into families. And yeah, along with Hagen and Jonathan Kirby, we were able to come up with a better proof of this statement. Okay, or a more general proof. So cool. This is then a way in which we now like bring the differential algebra into the complex numbers, and we use X channel in a very concrete way on the complex numbers. All right. Okay, so that's good about channel's conjecture, that X channel implies some form of channel. But this talk was supposed to be about existential closedness. So what do we know about existential closedness? So Jonathan Kirby proved this thing, which has been called a differential version of existential closedness. Suppose that you wanted to study existential closedness in the setting of differential fields. How would you go about that? Well, you take a differential field, again, characteristic 0, and you would consider a variety which is free and rotund. So here, it was important when I mentioned existential closedness that the conditions that you work with are geometric in the sense that they can be expressed over any field of characteristic 0. It should not mention, and it should not depend in any way on the topology of the field or the analytic topology of the field. So freeness and rotundity are purely geometric conditions that could be stated in algebraic geometry. So it makes sense to say something like this. And then what is differential existential closedness? Well, this time you're looking for points in your variety so that these points satisfy this kind of equation with respect to the derivation. Okay. And if you have a differential field, then you can always find an extension of the field, a differential extension, so that in that extension you can find points like this. So this time you're trying to find points in your variety whose coordinates satisfy the differential equation of exponentiation. Okay, that is differential existential closedness. And although the statement here is saying that there is a point, and existential closedness really cares about a Zariski dense set of points, because this works for every value of n, you get Zariski density from that. There is a general trick to get Zariski density out of this. So that's great. This is sort of like very close to Silber's conjecture, which is that on the complex numbers, this should be true. Freeness and rotundity should be enough. There is, however, a small, well, not small, but an important caveat. I mean, to some extent, this is as far as differential methods would take us to a full solution of existential closedness. Because one thing that the theorem does not say is whether or not this solution is made out of constants. And yeah, unless you impose further restrictions on the variety, there's just no way of knowing if the solution is constant or not. It could be, in which case you're not really found very much. So that would be like the, this is a limitation of just having to work in a differential field. That's like, okay, I can find solutions, but it's not super clear whether or not they're constant. If you strengthen your variety a little bit, then you can ensure that there will be non-constant solutions. But just like this in general, this general framework, then yeah, this is as far as you can get.
And here it's because you're taking the field extension F, right? Because if you were working with the exponential derivations, you still have to take this differential field extension, and you can't.
Yeah, exactly.
Thank you.
So okay, this is like another theorem that would make us believe perhaps that this Silber's conjecture is true. That yeah, freeness and rotundity should be enough. But if you wanted to settle this question fully and completely, then I mean, I don't think there is any way around it. Like, this really is an analytic question, and it should be addressed using analytic methods, because the exponential is an analytic function. Yeah, I think this is as far as we can get using, like, approaching the problem through the outside. Okay. Now, you might remember that existential closedness has an older brother, which was strong existential closedness, and which deals with having to get into generic points. So there is the original work of Boris Silber, and then there was further work which was like completed and refined by Martin Bayes and Jonathan Kirby, where they show that okay, you need to assume Shannon's conjecture. We know that that is one of the axioms that Silber said you require for understanding exponentiation. The other one was existential closedness. But Silber's original statement, the original way that he presented the argument, was you needed Shannon's conjecture and strong existential closedness. And the work of all of these people over a number of years in the end showed that you can take Shannon's conjecture, existential closedness, and then another conjecture called Silber-Pink from arithmetic geometry, and all of them together give you strong existential closedness using model theoretic methods. Okay, and well, if you care about Silber-Pink, or if you're very interested, here I've written down the statement, but it's an arithmetic geometry statement. So, and I also don't have a whole lot of time, so I will probably not get into the nooks and crannies of this thing. But I don't know, you might look at this and you might say, like, this doesn't sound like that good. I've certainly replaced like one conjecture with three conjectures. It doesn't sound like an enormous, leap forward. Is there anything that is certain about anything? Well, yes. So the point is that, okay, there is sort of this sums of conjectures give you other conjectures, and okay, but Axe-Shanwell, we've already seen, is able to provide a weak form of Shanwell. And there's another very important theorem, which says that Axe-Shanwell is able to provide a weak form of this Silber-Pink conjecture using model theory. And then the works of a lot of people which have produced cases of existential closedness. They have verified that in certain cases, existential closedness is true. Certain varieties which are rotund free do have a Zariski-dense set of points in the graph of exponentiation. And like I said, you require analytic methods to do this. So if you put all of these together, then here you have something certain. Suppose that you have a variety with a dominant projection to the first factor. So this is a stronger condition than rotundity. This ensures that the variety has points in the graph of exponentiation, as it turns out. That's not obvious. It requires a proof. Now, I also, if I want to try to get this differential existential closedness into the picture, you might remember that there's this issue that I don't know if the solutions that I find will be constant or not. So in order to address that, there is this thing that I say about V, which is to ensure that V has no CX factors. So what does that mean? This is a bit technical, but essentially what it means is that V cannot be defined over CX. Okay. And also these other varieties that you build out of V in order to define rotundity, those varieties also cannot be defined over CX. Okay, if that's the case, then, and the variety is free, then you are sure to not just find points in the graph of exponentiation, but you can find generic points with respect to any finally generated field. And okay, yeah, so this statement here is for sure, there's no conjectures or anything. And yeah, this is a combination of a work of a lot of people. And I don't think this is written down anywhere, but it should be hopefully soon. But yeah, so I think that's my time. Thank you all so much. Yeah, I'll stop here.
Thank you, Soledad. Thanks, Sebastian. So do we have any question? So let me ask one. For the proof of the exponential derivation, so you mentioned that it uses minimality. But do you expect that there should be a differential algebraic proof? Have you sort of looked at that, or do you think you do need?
Yes. Well, so in the case of exponentiation, at least I know that there is another way of doing it using only differential algebra. And that was Jonathan Kirby's original proof of the description of the field CX.
Yeah.
Which, well, okay, the proof essentially goes through trying to reprove access theorem, channel, and well, doing a few detours here and there, and eventually you can deduce that, okay, if essentially finding these exponential derivations, what you need to do is you need to start with, I don't know, some very small field, maybe Q or maybe Q bar,
right.
And you would then, starting from Q or Q bar, you would need to take like the trivial derivation here,
right,
and see if you can extend this derivation through different sequences of fields, so that at every step it respects whatever piece of exponentiation you can witness there.
Okay.
And that's how it goes essentially. That's how you build it up. To show that you can extend these derivations in this way, it essentially comes down to the proof, the algebraic proof of X channel.
Mm-hmm.
Now that we have an algebraic proof of X channel for the J function, for example,
right.
I can imagine that yes, you could also do it for the J function as well, a purely differential proof of the existence of such derivations.
Right. Thank you. That's awesome.
Yeah.
Any other question?
Do you have a concrete example of this result?
You want a variety, a concrete variety?
Right.
Yeah, okay. So for example, what variety can we write down? So any variety that you can write down in the following way will have this property here. So take some polynomials and suppose that the polynomials that define the variety, okay, they depend on x1 up to xn, but then the first one only depends on y1. And then the second one depends on x1 up to xn, and then it depends on y1 and y2, but not on any other y's, and so on. And then finally, the last one will depend on everything. And when I say it depends, I mean that it really depends, in the sense that this variable really shows up in this polynomial, and this variable also really shows up in this polynomial, and so on. So as you can see, like I'm building some kind of somewhat triangular system of polynomial equations. Then this kind of variety does have this dominant projection. And then if you choose these polynomials to not be over Cx, then it will have, it will satisfy that it has no Cx factors. So I can be even more explicit if you want. And I can write down I can write down the equations completely in some cases. So for example, if I write down x1 equals, let's say x2 equals y1, and then let's say n equals 2, so I don't have to write too much. And then I'm going to say y1 equals x1 equals y2 plus a. And here a is not in Cx. Then this variety does have this dominant projection over the first factor. If you have there are no relations between x1 and x2. So the projection to x1 and x2 is going to be everything, it's all of C squared. And with these two, then you immediately determine who are y1 and y2. And then there is this work of Branawell and Masser that says that these kinds of varieties have points in the graph of exponentiation. And because this A here is not in CX, then this V does not have CX factors. What I mean is that V is not definable over this field in this case. So this variety now has generic points of this form for any K. Is that a satisfying example, or?
What is Z here?
Well, you want me to find the points? So that is not so easy to do. The points are very transcendental, and writing them down is not, I don't know how to write them down in terms of anything that is like relatable. I know how to prove that there are points, but then showing you those points is a completely different, they might not be expressible in terms of things that are easy to write down, I think.
Okay.
All right. So I think let's take a quick break to the breakout rooms, and then we'll ask if we have more questions to Sebastian. But let us thank him again for his